Every failure tells a story, but only those who ask the right questions hear the truth. When a machine breaks or a process fails, most people ask, "What broke?" That is the wrong question. The right question is, why did the system allow it to break? Breakdowns, accidents, and quality failures cost the global economy trillions of dollars every year. But the real cost is not the repair bill. The real cost is ignorance. That's where root cause analysis, or RCA, comes in. In this masterclass, we are going to move beyond simple fixes and explore 10 powerful techniques used by the world's best engineers. From aviation safety to nuclear power, from healthcare to high-tech manufacturing, these are the tools that prevent catastrophes. If you are a professional responsible for solving problems, this is your playbook. Let's start with part 1. What actually is root cause analysis? It is a structured method to solve problems permanently. The key word is root. Think of a problem like a weed. If you snap off the top, it looks gone, but the root remains and the weed grows back. Correcting a symptom is temporary. Eliminating the root cause is permanent. Consider a pump that keeps tripping its breaker. You reset the breaker. It trips again. You replace the fuse. It blows again. You are fixing symptoms. A true RCA goes deeper. It answers 3 critical questions. What happened? Why did it happen? And crucially, what system change will prevent it from ever happening again? Part 2. The 5 Why method. This was developed by Sakichi Toyota for Toyota Industries. It is the foundation of modern problem solving. The concept is deceptively simple. You ask why 5 times. Not once, not twice. 5 times. This forces you past the obvious answers. Let's look at a classic example. The Jefferson Memorial. The stone was eroding. Why? Frequent power washing. Why? Lots of bird droppings. Why? The birds ate spiders. Why spiders? They ate gnats. Why were there gnats? Because the lights turned on at dusk, attracting them. The root cause solution? Delay the lighting by 1 hour. No gnats, no birds, no washing, no erosion. Part 3. The Fishbone diagram. Sometimes 5 whys isn't enough because there isn't just one cause. There are many interacting factors. Created by Kaoru Ishikawa, this tool maps causes into categories. We call them the 6 Ms: man, machine, method, material, measurement, and Mother Nature, or environment. Imagine a welding defect. Is it the welder? Maybe, but the Fishbone forces you to look at the material. Were the electrodes wet? Or environment, was it too humid? This is the ultimate brainstorming tool. It prevents tunnel vision where everyone just blames the operator. It forces the team to look at the entire system. Part 4. FMEA. Failure Mode and Effects Analysis. This is unique because it is proactive. We don't wait for the disaster. We simulate it. FMEA assigns a score to risk. We multiply 3 numbers. Severity. How bad is it? Occurrence. How often does it happen? And detection. Would we catch it before it hits the customer? This gives you a risk priority number, or RPN. You focus your limited resources on the highest RPNs. It's widely used in automotive and aerospace design. Part 5. Fault tree analysis. This is for high-stakes, complex systems. It uses Boolean logic and gates enter gates. Imagine a tank explosion. For that to happen, the relief valve must fail and the pressure switch must fail. If they are connected by an and gate, the probability is low. But if they are connected by an or gate, meaning either failure causes an explosion, the risk is huge. FTA maps these pathways mathematically. Part 6. Pareto analysis. The 80-20 rule. In any plant, 80% of your downtime comes from 20% of your machines. Engineers love to fix everything, but you can't. Pareto charts rank your problems. If you have 100 failures, but one type causes half the downtime, you fix that one first. Ignore the trivial many. Focus on the vital few. Part 7. Event and causal factor analysis. This is the detective's timeline. Failures aren't single points. They are chains of events. It started raining. The roof leaked. Water dripped on the panel. The breaker shorted. The fire started. You need to map every step to find where you could have broken the chain. Part 8. Barrier analysis. This is about defense. In a perfect world, hazards are contained. When an accident happens, a barrier must have failed. We often use the Swiss cheese model. Each slice is a barrier. Training, procedures, alarms, physical guards. An accident only happens when the holes in the cheese align. You must ask, did the barrier fail? Was it removed? Or was it never there to begin with? Fixing the barrier is often the fastest way to safety. Part 9. Change analysis. Stable systems rarely fail. If a machine ran for 10 years and broke today, something changed. Did we change the supplier of the oil? Did a new operator start? Did the weather change? Change analysis compares the incident day to a normal day to spot the difference. Finally, Part 10. Best practices. The tools don't work if the culture is toxic. If people are afraid of being blamed, they will hide the evidence. You must build a just culture. Focus on the process, not the person. Document your findings. And most importantly, share the lessons learned. RCA is a journey from reactive firefighting to proactive excellence. Start asking why today. Thank you for watching this masterclass. Now, go solve some problems.